Alright, so we've got a nice simple experiment to measure the efficiency of a microwave oven. We're going to be heating up some water. We'll measure how much we have, and then we can use the properties of water to figure out how much energy went into it when it went from a lower to a higher temperature. So let's start with just figuring out what we got here. I've got a styrofoam cup that we're going to be using, and I'm just going to zero the scale with the cup on there. So now when I fill it with water, the scale will tell us uh, how much water is in there. So just gonna dump this all in. It looks like I've got about 200 grams. That should be fine for this. So first thing we'll need to write down is the mass of the water. 201.29 grams. And then we need to know what temperature it's at. So the lab calls for tap water, but I'm actually using some ice water. There's no ice in it, it's just the water, but it's nice and cold, and that means it won't get quite as hot in the microwave, which I think will help us. Um, so this is my thermometer. The temperature in C here, it looks like it's about 7. We'll give it a minute and make sure that it doesn't change too much from here. Yeah, maybe we'll call that 6.95. It looks pretty close to there. So the temperature going in is 6.95 degrees C. Okay, now I'm going to take the lid off. Try not to take too much water out of the cup with the thermometer. Go ahead and put it in there, and I'm just going to run it for 1 minute instead of the 100 seconds. There's 1 minute. That should get it nice and hot. We have a nice sensitive thermometer, so I think that'll be plenty. So while we're waiting for that, one thing in the microwave manual, it says here the cooking power is 1250 watts. We're going to need that later. But also tells us the operating frequency of the microwaves. It's 2.45 megahertz. So, or sorry, 2,450 megahertz. So that's 2.45 gigahertz. We're going to need those later on, but I figured we'd just take a look at them now. Since the microwave is running. So let's see. Only got a few seconds left. Okay, so that was 60 seconds in the microwave. And I'm going to take my cup out and get the cap on there as quickly as I can because I don't want it to lose too much energy. I don't want to lose a lot of heat to the environment. So let me make sure the thermometer is in the water. Give this a nice stir. We can take a look at our temperature here. I'll switch back to the digits, but this graph is kind of nice because it tells us sort of when it's done changing. Actually, it looks like we probably want to pick something close to the highest temperature we see here because this water is at about 60 C, so it's going to be cooling off. Well, it might be reasonable to just take that flat line value, so let's do that. Looks like we're at 61.68. I know it just went down a little, but it's cooling off, so I'm going to say 61.68. T hot is 61.68 degrees C. So now we know how much the water heated up in the microwave, so we can calculate the temperature difference. and then we can calculate the amount of heat that went into heating up the water. So let's get that set up. Okay, since I can't record videos and use the calculator on my phone at the same time, what I got for the temperature change of the water is 54.73 degrees C. So now we can put together what we have to figure out how much heat went into the water. So it's going to be basically the mass of the water times that delta T times 4.186 joules per gram C. So if I take that 54.73, let's see, times 201.29 times 4.186, and that gets me, looks like about 46,000 joules. So the number I got there for the heat is 46115 joules. And now to get the power, we just have to take that number and divide it by the time, which was 60 seconds. So the power is 769 watts, it looks like. The units of power are watts, which is just a joule per second. So if you take joules divided by time, then you get power in watts. So if you remember, our cooking power from the microwave manual was 1250 watts. So the electric power in the microwave is 1250. And the efficiency is just the heating power, which we just calculated, the 769 watts, divided by the electric power the microwave used for heating. So divided by 1250. So if we take our 769 divided by 1250, it gets us about 0.614, 615. So about 61.5%. So that's not too bad, actually. The one thing to note here is the microwave uses more than just that 1250 watts. I actually have a power meter hooked up so I can see how much power it's using when it's running. And it was actually about 1.5 or 6 kilowatts. So it's more than 1200. It's more like 15 or 1600. But, you know, it's also got a, well, it's not powering the computer. But it's got a turntable and a light and a fan and a bunch of control electronics that it also has to power inside of there. So that's where some of that extra power is going. So if you wanted to calculate its efficiency as an appliance, you would compare it to the actual power it used. But here, since they tell us in the manual the heating power is 1250, the electric power for the heating element, that's what makes sense to divide by that. So finally, as a sort of bonus, we can calculate the wavelength of the microwaves. That's how long in space the actual waves are as they're bouncing around inside of there. And for that, we just need the speed of light and the frequency of the microwaves. So the frequency is listed here as 2.45 megahertz. I'm sorry, I did that again. That's 2,450 megahertz. So 2450 megahertz, but that's equal to 2.45 gigahertz. 2.45, sorry, getting a little crowded here. So mega is 10 to the 6 and giga is 10 to the 9. So if we take the speed of light divided by 2.45 times 10 to the 9, looks like our wavelength is about 0.12 meters or 12 centimeters. to 0. All right.